Okay, so let's have a second video on exponential functions now, and we saw all this game, some tricks, working around. So let's make sure, for instance, that we also, could, if given the exponential form in base e, then somebody might say, what's the half-life? And then we'd have to realize, doing some work, that the half-life is 7, right? So, in the first video, we were given this and found this, saw some relationships. How about if you're given this and find this? We also saw some of this other stuff in the first video. So, suppose that you've got in this, anyways, this is exponential functions video 2. In this, suppose we have y equals ce to the 0.099021 t, and we say, okay, what's the half-life? Or excuse me, this is exponential growth. If it had a negative, if it had been, matter of fact, maybe we'll just do these in parallel. Right? This is exponential decay, because it's got a negative there. And, your exponential decay rate is, 9.9. It's 0.099. Over here, it doesn't have a negative. This is exponential growth. And it's got an exponential growth rate, what's called the relative growth rate, right? The relative growth rate. Let me not call that, and let me call this relative decay rate, because this is more proper. This is relative growth rate of 9.9, 0.099, or 9.9%, however you want to say it. So what's the doubling time? Well, double is when there's twice as much as you started with. So those go away, and then the only way to write that exponent, because we need to solve for t here, is as a logarithm. The base on this log is base e, and this is the log base e of 2. So that's the ln of 2. So let's divide both sides by the 0.099. And now you're going to have your half-life, and it should be close to 7, maybe not exactly 7, because I rounded this to 6 decimal places instead of, you can only get so many decimal places though. So we got the ln of 2 divided by 0.099021, and it's 7.000 to 5 decimal places. See, it's 7. So t here is 7. So this is the half-life, right? This is the I'm sorry, I keep saying half-life. It's late. What can I say? I'm trying to help you guys out before your exam here. This is the doubling time. So, you were given the exponential function like this. They said, what's the doubling time? And so there it is. So that means you could write it as, y equals c times 2 to the t over 7 as well. We already saw, right? So you got to be able to go both directions. Similar over here. What's the half-life? Well, half, because this is decay, is when you have half as much as you started with. The c is going to cancel. You're going to write the exponent as a logarithm. And now you're going to divide by the negative 0.099. This is the log base e, otherwise known as the ln. So here then we got the ln of a half divided by negative 0.099021, and now we've also got 7, but this 7 is the half-life, because I use the same number, but here's negative, here's positive. This is the half-life. In other words, this function can be written as c times 1/2 to the t over 7, or you could write it as y equals c times 2 to the negative t over 7, for reasons I talked about in the first video. Because 2 to the negative 1, see the 2 to the negative 1, that is a half. So you got to be able to go in both directions. If I give it to you, with half-lives and doubling times, you got to be able to write it like this. If you're given to it like this, right? So there's a lot of information you can get. You just got to be able to translate between the two ways. How long until there's 60% of the original amount left? You could either use this or either of these, and it's going to be the same thing, 60%, right? That means you got 0.6 of the original amount. And you're looking for the time until that happens. Whoops, I forgot to write the C there, but we're going to cancel it out anyway with the C over here. And the C's cancel, and this exponent is written as a log base E. Watch, that'll be the same number as if I had done it right here and said, okay, how long until it decays to 60% of its original amount? Well, that means, that this is still 0.6C over here. And the C still divide out, and now the exponent is written as a log. Now this is a log base a half of 0.6. Well, now you need to change the base formula to say this is the log of 0.6 over the log of a half. Then multiply both sides by 7. And which numbers do you think are going to be exact to all decimal places? They're going to be exactly the same. Well, let me tell you something, maybe not to all decimal places, because here this is exact, whereas here this is rounded to 6 decimal places already. So I'm already picking up some rounding error in this one, but they're going to be pretty darn close. This is the ln of 0.6 divided by negative 0.099021. This is 5.15158. Just go 4 decimal. I mean, how many decimal places would you be going with time anyways? You'd be going out to like tenths maybe. But just to show that this is accurate for many decimal places, 5.1588 years or whatever the time units are until this thing is decayed to 65 or 60% of its original amount. By the way, another way they would say that is they say, how long until 40% has decayed away? Well, if 40% has decayed away, that means you still have remaining 60%, and you would do it like this. So now we got the log of 0.6 divided by the log of 0.5, and then you could have multiplied it by 7 first, it didn't matter, and we got 5.1588, of course, right? So, you should be comfortable using these exponential functions and translating from one to the other and from the other into the one, because they each have their uses.